So, now let this is 0, we know from Maxwell's equation. Now, forget about 0, if we put our formula, our obtained value of electric field, which is E0 and okay, E0 and H0, these are the amplitude, like this, these are the amplitude. Here it's not symmetric, but in case of wave it is always symmetric, same. So, E0 and e to the power minus I time omega t minus kr. So, this is okay. So, E0 is scalar quantity, we can take it out, and there will be I k, and again it will come e to the power minus I omega t minus kr. Just making the differentiation, we can write it k we saw a vector. Okay. So, it is 0, right, from Maxwell equation. So, we can write that k dot E is 0. Okay. So, we should keep in mind that k is the our wave vector which guides the direction of the wave. Okay. Now, similarly, if we consider that this is also 0 in case of vacuum, we are considering the vacuum. So, here also from here we can write, I am writing directly, this is, so k dot H is also 0. So, again considering another two Maxwell's equation, we can prove that simultaneously. This is, let us say 1, 2, the third one will be and the fourth one is. So, these are also Maxwell equation, but considering the in terms of wave vector. So, this will be minus omega epsilon naught. Okay. So, these are the 4 equation. Okay, what is omega? Omega is our angular frequency. How it is related? Omega equals to c times k. Okay. Again we can write that if omega is c times k, then k is actually 2 pi by lambda. This is most general form of wave vector. Lambda is the wavelength. Mind it, omega is the angular frequency, not the frequency. Frequency is nu. Nu is actually c by lambda for any wave. We are considering electromagnetic wave, that is why we are writing here c. Okay, c is the speed of the light or the wave. So, now what are the outcome of this waves of this equation? 4 equation we obtained that. The first equation, this equation what it says, it is the dot product of the wave vector and the electric field, and that is 0, which means that electric field and the wave vector is perpendicular to each other. Similarly, wave vector and magnetic field also perpendicular to each other. So, electric field and both the wave vector is perpendicular with both electric and magnetic fields, but it does not mean that electric field and magnetic field also perpendicular, that may be in the same direction, but from this equation or this equation both are same, we can say this is k cross E. So, from here we can write that okay. So, in case okay, this is actually k cross E means it creates a plane. Okay, we can think like that, that will be more easier. So, k cross E, k vector cross E vector, and here is the H vector. So, k cross E is not non-zero, it is equal to mu omega, the direction of this k cross E is in the direction of the magnetic field H. So, from here we can write that H vector, the magnetic field, is actually proportional to, not proportional to, perpendicular to k times E. So, here, so we can from here say that H is also perpendicular to plane containing k and E. Okay. So, from here we can say that all three, K is perpendicular to H, perpendicular to E, and also H is perpendicular to E. So, all three are perpendicular to each other. Okay. Then what will be the structure of our wave? Let us say this is our z axis. So, this should be x, this should be y. Yes. Okay. So, now let us say this is the direction of propagation. Okay. And in x direction, so then the wave will be this is the electric field. So, electric field should be perpendicular to the direction of propagation. Propagation is z. So, actually k vector is along z axis. So, now electric field E is perpendicular to k, it is working along y axis, and the magnetic field, it is also perpendicular with the both k and E, it along x axis. So, this is the electric field and along here. So, we can use the different color. So, this is our this is magnetic field. So, this is the structure of electromagnetic waves. We can so this is electric field and this is magnetic field. So, we can see here both electric and magnetic field are oscillating fields. So, this oscillating electric fields is generating the magnetic field which is in perpendicular with the direction of the electric field, and again the generated magnetic field also is oscillating field that create the electric field in perpendicular direction. So, that is why again that consecutively electric field and magnetic field produces each other, and the electromagnetic waves propagates in the direction which is perpendicular with both electric and magnetic field along the z axis here. Okay. So, one more thing we have to discuss here. So, considering that equation k cross E is omega mu naught. So, this was the equation. So, from here we can write that omega mu naught, and also k is kappa times n cap. So, we can write is kappa omega mu naught here n cap E. Okay. So, again what was the form? Omega equal to c times. Okay. So, we can, so this can be written as c omega naught. Okay. Again c is 1 by root over this. Okay. So, from here we can write that it is also equals to c epsilon naught n times E, and again H mu naught H equals to B. So, here also we can write here this is okay. So, this equation essentially leads to that magnetic field B is equals to okay. So, from here also we can see that magnetic field is also the perpendicular of the electric field, because n is the direction of propagation, E is the electric field. So, there is a cross product. So, from here also it is proved that magnetic field is also perpendicular to electric field. But one thing we should notice here, so we can write that E by H, the mod of E by H, or B we can write also, if it is, let us say it is B not H, the mod of E by B equals to E naught by B naught, because that the mod is considered. So, here we can see that the magnetic field is much more weaker with respect to the electric field, because there is a C, and we know the value of C is around 10 to the power 8, 3 into 10 to the power 8. So, this is actually C. So, this is very important relation, that electric field is C times stronger than the magnetic field. Okay. So, this part is clear. Now, for any waves, that may be electromagnetic waves, that may be mechanical waves or sound waves, the basic relations are C is equal to nu times lambda, that we are considering the electromagnetic waves, that is why we are writing C here. This is our frequency and this is the wavelength. So, how this Maxwell theory, Maxwell propositions were verified, that is the important thing. How we can say that yes, Maxwell was correct or not. So, for that some experiments were there, were done by other scientists like Hertz, Jagadish Chandra Bose, Marconi, these scientists done the experiments. So, how the experiments were done, let us consider one charged particle is oscillating. So, there is a oscillating frequency, let us say this is the oscillating frequency nu. Then we, as we see, as charged particle oscillates, then what happens, around the charged particle there is a electric field. That electric field will also oscillate, which creates the magnetic field, oscillating magnetic fields, and that oscillating magnetic fields again create the electric field. So, essentially it generates electromagnetic waves, and the frequency, oscillating frequency of that charged particle is equal to the frequency of electromagnetic waves. Okay. So, for now we are saying that light is electromagnetic waves a thing. So, we can make experiment considering our light. Let us say if we consider the yellow light, the frequency is 10 to the power 14 hertz, around 10 to the power 14 hertz. So, this is very high frequency. So, experimentally this frequency can't be created. So, dealing with if we want to deal experiments with the yellow light, that is not possible. That is why generally experiments are done with the radio waves. Okay. So, in case of radio waves, the frequency is much more less, we can produce that radio waves. So, in that time Hertz, I do not know the exact year, okay, that is 1887. So, Hertz produced that electromagnetic waves considering that radio waves basically, because the frequency of the radio waves is very less. So, that can be produced. Later Jagadish Chandra Bose and Marconi was succeed to develop the propagating radio waves of much more higher frequency, 5 nanometer to 10 nanometer scale. Okay. So, that is okay. This was the experimental background. Now, what is the range of our electromagnetic waves, that we have to understand. Okay. So, frequency and lambda, these two are very important parameters. We are considering C equals to 3 into 10 to the power 8. Mind it, this C is in vacuum obviously. What happens in other medium? This equation is valid, and this should be less than 3 into 10 to the power 8 meter per second. Okay. Because in vacuum it is mu 0 epsilon 0 and mu r and epsilon r is there, which is greater than 1. So, that is why this will be less than 3 into 10 to the power 8. Okay. So, here now nu and the lambda. So, in terms of nu and the lambda, okay. So, first is our cosmic ray in terms of okay, frequency. If we write, the frequency of cosmic ray is maximum. After that X-ray, after X-ray it is ultraviolet, then visible, infrared, okay, after infrared, how here, microwave, and then short radio and okay radio. So this is our electromagnetic waves in terms of frequency. So in lambda it is just reverse, because we know that nu is equal to c by lambda. Okay. So in details we can write here, that is drawn in NCERT book as well. So I am just writing it. For cosmic ray, what is the frequency? Okay, frequency is around 10 to the power 30 hertz. Okay, next is okay. Oh, between this there is a gamma ray. Okay. Next is our gamma ray. The frequency of gamma ray essentially 10 to the power 22 hertz around. It's actually varies from 10 to the power 19 hertz to 10 to the power 27 hertz basically. Okay, so we can briefly say that around 10 to the power 22 hertz. So next is our X-ray. The frequency is around 10 to the power 15 hertz. Next is our ultraviolet UV ray. Okay, it's 10 to the power 15. It's 17. It's 15 hertz. Next, visible range. The frequency is okay, and microwaves. And radio wave has a very large duration, like it's 10 hertz to 10 to the power 8 hertz around. So this is the scale, and in visible we know that this varies from violet according to picture. Red is around, the wavelength of the red light is around 700 nanometer. In case of violet it is okay. So this is our electromagnetic waves. So now at last summary. So what we studied, that first we discuss about our electric field. What is the electric field and magnetic field? Okay. Next we studied after electric field and magnetic field. Here first we discuss the electric field, magnetic field. Here just we discuss the 4 forces, and after that electric field and magnetic field. Next we discuss our Lorentz force and Maxwell equation. Okay. So here we discuss how the electric field and magnetic field define, then Lorentz force and the Maxwell equations. These Maxwell equations consist essentially 4 equations. Now after doing analysis of Maxwell equation, we evaluate the form of electromagnetic waves. In vacuum this is 4 Maxwell equation, and then we obtain the wave equation, and then we obtain the E and B, also K is the wave, also K, which is kappa times n, and from there we just, after analyzing the form of E and B using the Maxwell equation, we derive the form of electromagnetic waves. Okay. So, this is the summary of our first class. So, in next class I will discuss the integral forms, not discuss, I will write down the integral forms which are actually the same, the meaning of the integral form also same with the our differential form, but the notations are different for integral forms of Maxwell equation obviously. Okay. And also we will discuss in details about our spectrum, electromagnetic wave spectrum, and the parts of the electromagnetic wave like radio wave, microwave, and visible light, all of the things that is we will discuss in the next class. So, okay, thank you.